Okay, let's begin our conference. So good morning, everyone, for those in the US, and good afternoon to those in the UK. Welcome back to our BHK technical conferences after taking a 2-week break. We're now in the second round of our technical conferences, so we'll focus mainly on collaborations and updates. Thank you all for those who signed up for a time slot. And because most people signed up for time slots in July and August, we'll be having presentations on updates for today and next week. And today we'll have just one presentation today.
Vincent, it's very hard to hear you so you're fading out. Are you close to the microphone?
Yeah, I'll repeat that. Can you hear me?
Oh, I'm sorry. Okay, we switched microphones.
Oh,
Can you hear now?
can you hear now?
Yes, much better.
Hello?
Yeah, better.
Can anyone hear me?
Yes.
Hi. Can anyone hear me?
Yes, we can hear you now.
Yeah, I can see the.
I think Vincent can no longer hear. The rest of them haven't connected his speaker.
Oh.
Okay. All right. So,
Hello. Can everybody hear the audio?
Yes.
Okay.
Okay.
Great. Thank you.
all right. So I'll repeat that. So yeah, welcome back to our BD2K technical conferences after taking a 2-week break. We'll be starting our second round of technical conferences, which will focus mainly on collaborations and updates. And thank you for all those who signed up for a time slot. And if you haven't already, please fill out the sign-up form. And because most people signed up for slots in July and August, we'll have presentations about updates for today and next week. So the collaboration conferences will start late June and early July. But today we'll have just one presentation, which will be about Reactome updates, and we'll also get more of a technical understanding of Reactome. We're scheduled to start around 8 and end at the latest 9 a.m. Pacific time. And again, these conferences are recorded and can be accessible online once we've processed them. If you have any questions during the presentation, please type it in the message box. Also, please mute your mic during the presentation to prevent any background noises. Are there any questions before we begin? Okay, so we're going to begin with Antonio from Embo EBI, and today he'll be presenting about Reactome, about his updates, and also technical overview of Reactome. All right, go ahead, Antonio.
Okay, but do you mind? I mean, I need to share my screen, so please.
Okay, so
Can you see my screen?
Yeah.
Yes.
In your presentation.
Okay, I don't. I don't see now if you ask any questions because both screens have been filled with the presentation. But let's keep it like that. And if you want to interrupt me, no problem.
Oh, we just lost the.
Tell me if you can see now the presentation, please.
Well, we just lost your PowerPoint.
Okay. Let's see if I can find.
Yes, now we can see it.
And now it's full screen.
No.
Can you see full screen?
We see the PowerPoint application, but not the presentation.
Yeah, we just lost it again.
Yes, I'm trying to switch it off and on. Okay, now you should see the PowerPoint again.
Yes.
And now I will. Can you see
Yes, that was
the
fine.
full screen?
Yes.
Okay, so let's start with this. Okay, well, so thank you very much for the chance of presenting the technical side of the Reactome project. So today I will talk about the pathway browser and a little bit more how we developed it. Then we will talk a little bit about the analysis tools and later on the pathways overview. And most of you will know it as the firework. And at the end, I will explain you a little bit about the cells, the sonar-based cells in Reactome. So, okay, starting with the pathway browser, as most of you probably have used it, it's a tool just for visualizing and interacting with pathways data coming from Reactome. And the challenges that we had when we started developing this new version was to deal with the modularity and long-term maintenance, because we wanted to create a tool just to last for long. And we also had as a challenge to keep a system of state and history management. So every point in Reactome can be linked from the outside in the pathway browser. Every state has a URL that points to it. Then another challenge is, of course, the memory usage. Since this is a web application that we hope the users keep using for long, so the sessions will last longer, we have to have a very good memory usage management or memory management, because we want the application to run as fast as possible for the whole session. Since the pathway browser is completely modular, or we were challenged to create a completely modularized application, we had to create a system just to synchronize all the events coming from different modules. And of course, we needed a way of being able to integrate third-party widgets from other resources, because we wanted to show information coming from other resources just integrated next to the views of the pathways shown in the pathway node. Okay, so just modularity versus long-term maintenance. The problem that we had is that the initial development time and the new features that we can use or we can introduce in the future, we didn't know at the beginning. So to handle, as it is in every large-scale application, because all of them have their hardware. Sorry. So the best way of face this problem was using a design pattern that create the compartmentalized areas of responsibility. We had the different options at the time, but we chose to use the model view presenter. So the model view presenter contains 3 different parts, as the name says. So the model that encompasses all the business objects, or basically where the data is held. Then the view, that is where the user interface components that is basically what the final user sees from the usability point of view. And then the presenter is the part that contains all the logic for the application. So it's a way of encompassing the model and the view. So taking data from the model and asking the view to show some data, and also receiving events from the view and doing actions in the model if it's needed, or sending events to the event bus just to notify other modules in the application that something has happened. We also had for example, in the part of the presenter, we also have the history management, the view transition, and data synchronizations that, as we will see in the next slide, these are not modules, but we call them managers. But let's see. So, model view presenter decouples development, allowing multiple developers to work simultaneously, and that is also very important because we can have several people developing different modules, and we don't want to be tied one each other. So we want to have independence, so everyone working as its pace, and MVP was a very good way of doing that. So the pathway browser has the event bus as the main or central component, and then has 6 different modules, which are the hierarchy panel, the test panel, the top bar, the diagram, the fireworks, as we will see as the pathway overview, and then the analysis tool. Every of these modules don't know the existence of the other, but they all communicate via the event bus, sending and listening to events. There are also 4 managers. The difference between the managers and the modules is that managers doesn't have view associated, so the user won't see anything, but this is running behind the scenes, doing what it needs to be done. Like the state manager is the one checking, of course, as the name says, the state of the application. The fellow is the one that helps us to go from one species to the other. Then the data manager is the one in charge of returning the information only once, in case the information is needed in the future. It has to be kept in somehow and provided to the modules when they need it. And then the Google Analytics Manager, that in our case we are using Google Analytics, but this is tracking the event bus, sniffing the event bus, and when there are events that are worth sharing or notifying to the Google Analytics just to have the proper reports in the future, then this is done by this manager. Okay, so this was about the pathway browser. A little bit talking about the development, but without getting so deep in code or details. The analysis tool is the next of the projects that I'm going to talk about. First, I will start explaining the analysis tool as a web service, and later on we will see how it works integrated, or we won't see how it works integrated, but I will show you how it was integrated into the pathway browser. The analysis tool is a pathway enrichment and expression, and contains a pathway enrichment and expression analysis as well as a species comparison tool. When we started developing this tool, the challenges for us were to develop a reliable and stable application. We wanted this application to produce results with a very competitive, competitive response time, in the way that it could be introduced in different pipelines, or just to be used for the final user being integrated in other applications. Then we also wanted to offer results in Reactome for every species that we have, not only for human, but at the same time we wanted to be able to offer the possibility for the users to send data belonging to different species, like proteins belonging to different species, and then project all of them to the same one, to human, and see the result all together in this species in human. At the same time, as one of the requirements, we were aiming for a topology-based analysis, starting with a very basic approach where we were counting just the number of reactions hit per pathway. And the last of the requirements, of course, was to integrate this analysis tool into the pathway browser. From the development point of view, this is how the analysis tools look like if we dig a little bit deeper. On the server side, very low, we have the Reactome database. That is the database containing all the Reactome data. And just on top of it, we have developed the analysis core that has 2 main modules that are the builder, which just reads the Reactome data from the database and builds an intermediate file containing a radix tree for the identifiers lookup, a graph for all the entities, complexes, and sets that we have in Reactome, and finally a double link tree just to represent the pathway hierarchy. This file represents all the data that is needed just to perform an analysis, but the size of these files is suitable to have it later on loaded in memory, so we can perform all the analysis based only in memory, so without having to access to the Reactome database, and that is what in the future will give us the speed that we can achieve for the analysis. This builder runs only once per release, and then this file is kept, so when we just run the analysis service, the core loads this file and loads it into the analyzer. That is the one that is used by the analysis RESTful service, as we can see. I don't know if you can see the mouse, but I'm just now pointing to the arrows that are showing this information. So the analysis RESTful service uses the analyzer, and the analyzer is the one loading the file. The analysis RESTful service is the interface for the tool to the outside world, and then there can be clients. In our case, we develop one that is integrated in the Pathway browser, and this can be all accessed via RESTful services. Our RESTful services is token based. That means that every analysis request has a token associated. In the future, the user can just use the token API, the token method, sorry, of the API, just to retrieve or to dig deeper into the result of the analysis without having to send the data once and again. These tokens are insured for a minimum of 7 days. After these 7 days, they get into a least recently used queue, and it depends on the usage of the token. If it's strongly used, then this result will live longer. If this result is not used, then when the LRU decides, it will be just gone. At the same time, we are associating the MD5 of the submitted samples to. We are mapping the MD5 of the samples to tokens. So in case the user sends several times the same file during the one release period, we won't analyze twice the same file. So we will know which is the token associated, and we will retrieve the result associated with this token. Okay, so this was about some technical details of the pathway analysis, and now I will talk a little bit about the pathways overview. This is the project that we call the Fireworks, but let's go deeper and see how it was and how we developed it. So the pathway overview is a genome-wide hierarchical visualization of pathways in a space scaling graph. And the challenges we had at the beginning was, of course, finding a nice layout which fulfills all the initial requirements that we had. Fireworks, or the pathway overviews, we want to have a different one for all the species in Reactome. And then we wanted to keep the same look and feel across species, so we will see that in the next few slides. Then another challenge was to implement the widget, taking into account that the result will be like a huge number of nodes to be shown on the screen. And then we knew that at the beginning, we knew that depending on the number of elements that you want to display, and depending on the technology that you decide to use, it will be, let's say, fast and nice for the final user or not. And of course, as everything that we do in Reactome, we wanted to integrate it into the pathway browser. Well, this slide, it's the only difference with the first one, with the previous one is the aim. So the aim is visualizing a genome scale pathway analysis result and allowing both a quick first glance and a rapid zooming in on these interesting results. So the pathway overviews, or the Fireworks, is not only to see all this pathway relationship, but also to display the results of the pathway analysis in a graphical way that makes it easier to understand for the user those areas of Reactome that have hit by the sample that is used for the analysis. The requirements, as I was talking about the requirements a couple of slides before, but let's go and see one by one. So the first is that we want to clearly show all the Reactome pathways and their parent-child relationship. We want to have a structured view, easy to follow and intuitive for the final user. The idea was that the size of this node is proportional to the size of the represented pathway, and that's very important because in Reactome, not every pathway can have a different number of proteins or a different number of entities. So for the larger the number of entities is, the bigger the size of the node. At the same time, we wanted to avoid duplication of the nodes. So if a pathway is several times in Reactome because it's an encapsulated pathway and has a role into different places at the same time, we only want to have this node once and have as many links as interactions with other pathways this pathway has. But at the same time, that will create a lot of edges, and we wanted to minimize the number of crossing edges. Then the next requirement was that for every node, we should keep the same position in the view from one for the, let's say, next releases. So when the user has like a set of favorite pathways that is working on, in the next release, we don't want these pathways to completely change location in the pathway browser. We want these pathways to be, if not in the same position, as close as possible, because just in case there is new data that is added next to these pathways, they have to be moved, but we are aiming to move them as less as possible. And finally, the last requirement, and I think one of the most important ones, is just to show the analysis result overlaid on the pathway overview. So, when we started to develop the pathway overview, of course, we didn't have a clue of how we wanted to show, but we knew what we wanted, but we didn't know how we wanted. So the first thing we tried was, of course, a force-directed layout that we could execute for different period of time. So this was the result for 1 minute, this was the result for 5 minutes, and this was the result for 10 minutes. Benefits and problems. The benefits are the algorithm already exists, so that's great. We don't need to develop a new one. And also, we can see it as a benefit that we can choose the time of execution. So we decide for how long we want this running during the release time. But the problems is that the nodes don't remain in the same position across different executions. So in different releases, the nodes will end up being in probably complete different places. That wasn't fitting our requirement. Next idea was fixing the top-level pathway into a grid and leave the force-directed algorithm for 10 minutes. But as the same as before, in this case, we can only ensure the position of the top-level pathways, but not the rest of the node. And the same happens if we, instead of a grid, decide to place them into a circumference. What made us think, what forced us to change the approach and just develop. So we came up with our own radial layout, and at the beginning we thought to just place in the first ring all the top-level pathways, and in the outer rings to represent all the children, with the benefit, having as a benefit that the node's position can be kept across releases, so that was one of our requirements, but the problem is that this doesn't optimize the available space. In a rectangular viewport, that is what we all have in our computers, we will have a lot of, it will be very crowded in the center of the screen, and in the corners, there will always be empty space. So this wasn't really nice to have all the information in Reactome to be shown. Then we thought, okay, let's go a little bit further, and what is going to happen if we have several bursts instead of one? And what happens if we, in the center of each burst, we just represent a top-level pathway? And then what if each concentric ring now per burst is representing all the children of the previous ring? And then the result was this, that despite of the edge crossing, it starts fitting with all our requirements. And then just by rearranging the position of the top level pathways, we just came up with this layout where we are minimizing the number of crossing edges, and we are filling all the space, and we are clearly showing the relationship, the parent-child relationship of all the pathways in the Reactome hierarchy. Now, when the user submits data to the pathway, the pathway analysis, we can overlay the results into the different bursts to show those areas in Reactome that have been fit by the sample. In this case, we display the result of a representation. This would be the result of the expression analysis, where the user just provides a set of proteins and then different columns with different expression values, and we use this very nice rainbow color just to show these expression values for those pathways that are significant in taking into account the sample. And we do the same for the species comparison that, as I explained before, is one of the options of the pathway analysis. Something that is very nice in the Fireworks implementation is that depending on the depending on the level of zoom, we show more or less information, and that provides a visual feedback for the final user. And well, just tell you that the code, both of the layout and the widget, are available via GitHub, and the integration in the pathway browser is as it looks in here. So we just place it where the diagram is, and we have a mechanism just to switch from Fireworks to the diagram and back. Another of the requirements was the other species layout. The image that you see now on the screen is just for the Homo sapiens pathways. And for example, if we switch to Plasmodium falciparum, we will see that most of the pathways are gone, so they don't exist, or they cannot be inferred into this other species. But for those that remain, for those that can be inferred, we keep the same location. So when the user has a favorite pathway, it's very easy to identify whether this pathway has been inferred to the other species or not, because it's in the same location. It happens for all the species, but I'm just showing this example. About the implementation of the client, probably is the most interesting bit here. Now, taking into account that the layout is a big chunk of it. So just let you know that it's an HTML5 canvas, it's not SVG, even though it looks like an SVG, but it's not. It also follows a MPP pattern as the same that I explained in the pathway browser. It contains different modules, and every module is completely independent of the other. So we have the canvas that is at the end is an HTML5 canvas aggregation, just to have all this visualization speed up. The viewer manager is another module. The main control panel, thumbnail, legend, controls, and settings. This is all different modules that are running at the same time in the implementation of the widget. We also integrated animation to and a system to have this time series progression. So when the user submits analysis data with expression values, and the interesting bit is that now it can be played, and all the time series will show one after the other, and this is all done thanks to this progression. Then we also use we use quadratic cubes to represent the edges going from one node to the other, and we also offer visual feedback when the user hovers the mouse on top of this. And the nodes and the path are selectable, and this is useful. The nodes is completely understandable, but the paths are useful because when hovering a node, it's very easy to identify in which bursts or in which top-level pathways this node is, and this is giving a very good visual feedback to understand the role of every pathway. Going a little bit deeper into the implementation of this Fireworks. just explain you that we are using a two-dimensional space partition with a data structure that is called quadtree. And this quadtree is a data structure used to divide this two-dimensional region into more manageable parts. I will show you now how it works in the next slide, but I thought it was a good idea to show a couple of definitions. So the quadtree is a way of partitioning this space, so it's easy to traverse and search into the space. And then it's for the developers, we have to understand it as an extended binary tree that has 4 children instead of 2. The quadtree, imagine that we divide the space of the viewport or the canvas in 4 regions. And now we decide that in every region we don't want to have more than 4 objects. So the first object now is included in the second region, but if we keep adding more objects in this second box, we see that there are no more than 4 objects per section. But if we keep adding objects in the second section, we need to split this section into a smaller section. So now the section 2 has 4 regions, 4 subsections, and each one of these doesn't have more than 4 elements on it. And this has to be done recursively when new objects are added into the viewport. Taking this example to, let's say, expanding the example using more nodes, we see how the plane would be divided into smaller subsections following the same approach that I explained before. In this case, let's imagine that the user has the mouse here in the yellow section, and we want to see whether the red dot is or not hovered by the mouse. This is important. Let's step back. Let's step back for a second. Why is this important? This is important because in Canvas we don't have a way to identify the object that the mouse is hovering in the canvas, because this is not like SVG. SVG tells you when the mouse is hovering or clicking an object that you are directly representing in the DOM. But in Canvas, you just have the canvas, and you have to understand the canvas as something that you can draw on it, but there is nothing else but the position of the mouse for a certain time. And now we have to find a way of having a correspondence between the mouse position and the object that is being hovered. So this is the reason why we are using the quadtree. I just missed the explanation in the previous slide. But now, taking this into account, let's imagine that the user is hovering this red point. In the classic approach, we could, for example, think, okay, we can just iterate of all the objects in our model and ask whether they are being drawn in the position where the mouse is. So one by one, we just ask every object, are you hovered by the mouse if the mouse is in this position? But this is a brute force algorithm, and this is not scalable because, well, it's not scalable, but it's very slow, because we can end up just checking all of the objects in our model. So by the quadtree now, what happens is if the mouse is in this position or in this section over here, first of all we compare the position of the mouse with the center of the viewport, and then say, is from the first horizontal line, is the mouse on top or below? Now the answer is below. So in this first jump, we can just say that we don't care about any object that is in the upper side of the viewport. Now we compare the position mouse with the central vertical line, and then is on the left or on the right. In this case, it's on the right. So we already know that we have to only focus on those objects that are in this quadrant, in the fourth quadrant. Doing the comparison now against this point, against the center of the fourth section, we ask again up, down, left, right, and if we do that like 5 times, we will find here that we can go from this node of the quadtree to this node. So this the first step, then the second step would be going to this other section, third step to this section, fourth step this section, and the fifth step would give us the box that contains only 2 objects. Now asking only these 2 objects whether they have the mouse on top of them or not. So instead of comparing against all the objects, we just compare with two objects. So that will give us a very nice response time. And this is how we do the correspondence between the mouse position and the objects placed in the canvas for the fireworks. Fireworks is integrated in the Pathway browser. And I think in the past I just showed you a demo, but we can go for it later on if we have time and you want to see. The last of the projects I wanted to talk about is the search. This was developed by Florian Korminger. He came to Reactome for 6 months last year. And the search right now looks like this, where for a given search, like for example P10, we show the results, showing also some phase setting on the left-hand side, and by clicking, for example, on the third result, we display or we show the details for this entry. The new search, the new Reactome search, is based in Apache Lucene Solar, and the challenges for us were just to develop a fast data accessibility. So for us, the challenges were fast data accessibility, accurate search, of course, and incorporation of various different fields for searching that we didn't have in the previous implementation. Of course, Solar for us was good because it's a high-performance, scalable, full-text search engine that is specifically designed to search through large data sets. If you configure Solar to meet your needs, it will probably fulfill all of your requirements, and at least in our case. The specific features that were included in our case are filtering, result grouping, fit highlighting, spell checking, and auto-suggesting, and all of these features were very well welcome for our users. And well, there are 2 separate programs created from scratch. One is the indexer that is run once per release, takes the data from the database, and create all the Solar documents that are included in the Solar engine. And then later on, there is a searcher that takes advantage of the Solar service and just presents the data following our template, as I showed you a couple of slides before. These are the fields used to create the Solar schema. I don't want to go through all of them, but just for you to understand that first you have to create a schema, and later on create an algorithm that reads the data from the database and fills these documents following a precise schema. And then in our pipeline, as you can imagine, when a search needs to be executed, then we first take advantage of the Solar search. Then we just get the data and filter and use a template just to have the result page. And when this result page, the user selects one of the entries that is interested in taking into account the summary that we show there, then is the details page that is feeding from the database. And now it will show more details about the selected item. And yeah, that was it. So thank you very much, and I would be happy to take any question. Thank you. Now is when you say that I was mute.
Yeah, thank you, Antonio. Are there any questions?
Yeah, I have one. This is Andrew here. So, really great stuff. Obviously, I love it. So, question. Part of my, can you talk a little bit about the pathway analysis and the enrichment analysis of Dean lists, and how often, whatever usage metrics you guys have.
The usage that we have.
Yeah.
Usage methods or usage?
Usage metrics.
Metrics. Oh.
Okay. So in terms of let's say usage report.
Just the analytics.
Okay. Well, right now I don't remember the number.
But the specific number doesn't matter. So let me tell you what I'm thinking here, right? I mean, there are obviously many tools online that do sort of enrichment-based analysis. And in my mind, right, I decouple the two parts of this. One is sort of the reference set of gene lists or pathways, and then one is the analysis methodologies and the statistics and so forth, right? And I, to some degree, right, I wonder, you know, I've always thought, okay, well, it would be great if there were sort of just best practices or just reference implementations of one of the other that allowed you to integrate across many other things across the community. So, for example, right, you know, if you spent a lot of time optimizing the enrichment analysis and you know, the analysis part, and it currently works on Reactome pathways, what would it take to actually extend that to, you know, gene ontology terms and to KEGG pathways and to other gene lists that might show up in COPA KB or in BioGPS?
Actually, that's a very good question, and it's nice that you ask it, because I had this very same conversation with a guy in the not very long ago, because he was asking exactly the same. He's like, okay, now you have a very fast analysis algorithm, but can we use that algorithm with our data? The first answer, okay, that pops out of my mind is no. Why? Because when we develop this algorithm, we just feed the algorithm with Reactome with the Reactome database, so it doesn't take the data from any standard. Okay, so the part of the algorithm that builds this intermediate data file is just querying directly to the database. But it would be nice in the future just to create a mechanism to have a format that people can put the data in this format, and this can feed the first step algorithm, the builder, and then this builder just takes this data, builds the memory-based approach, and this file can just be used later on for the analysis. So this is a very interesting project to do. If I had the time, of course, I would do it. But yes, that would be good. The answer to your question is right now, no. But it would be.
The algorithm also takes into account a number of these, well, let's say, non-standard features of Reactome, like it is a hierarchical pathway database. Many pathway resources are just flat, and the hierarchy is a major factor in the algorithm. So that's one of the things. Of course, Go is also hierarchical, but that's a bit different. But in terms of pathways, that is one thing which is makes it non-standard. But otherwise, yes, what Antonio said is absolutely correct. So it might be nice, but at the moment we haven't worked on that.
About the first question of usage, if you are interested in numbers, I can tell you that last April it was like 9 or 10 months that the analysis was put in place, and we reached like around 360,000 analyses, which is not bad.
Yeah, that's not bad indeed.
What we've seen is we have had an analysis tool for years, which was very fragile, the predecessor to this, and irrespective of absolute numbers, what we've seen is a very marked increase in the usage of the analysis tool. So it's clear that with the much better performance, really usage has increased a lot, which frankly is not that surprising because the old one was really clunky, in all honesty, but that was very visible in the statistics also.
Yeah. You know, part of the reason I wonder about the usage statistics is because, right, the tool we all love to hate is David. Right, and lots of people outside of sort of the, you know, bioinformatics, genomics community, right? People, you know, it's like the average bench biologist uses David a shocking amount, right? And of course, it's a horrible tool from a data standpoint because, right, the data are very old in it, right? Gene ontology terms haven't been updated in 2009, since 2009. I'm guessing, right, the protein domain definitions are probably similar. And anyway, the data are very stale, but why do people use it, right? Because the visualizations are not bad, and it does integration across many different domain areas, right? Again, protein domains, gene ontology, pathways, and so on and so forth. And so that people see it as a one-stop shop. So, that's where I wonder, as good as your usage metrics are, truthfully, it's a shame, but I bet David's usage is an order of magnitude higher.
Yeah, it's possible, but you also have to take into account that well, yes, I mean, yeah, I completely agree.
But that's not a reason not to have a good tool. I mean, these things no. David, at some point had lower usage and then got used because people liked it. And so clearly we see an increasing trend. If it will ever reach that level is a different question.
Yeah, and I want, I would love any tool to displace David. And so I guess my question is, right, in order to do that, right, is sort of the idea of data integration beyond Reactome, is that something that would, make a quantum leap in usage of your analysis tool? I don't know. I'm just throwing out there as an idea.
That is actually part of what we have already concretely proposed in pending proposals, and also what will happen in part in BD2K. So we are going to integrate interaction data into the Reactome analysis, which means we will enhance the coverage of Reactome by the broader coverage of, say less precise intact and potentially other interaction data sources. So that's already, and this will be taken into account in the analysis tool, and this will be also then available in the search and in the visualization. That's what we are currently setting the basis for that by redeveloping the pathway visualization. But once that is done, then we will move on to the background algorithm development.
Cool. Henning, since you mentioned it, I mean, what happens when you try to shoehorn the gene ontology structure into this?
Well, as Antonio said, it would be a very significant project because he played with, for example, exploiting the structure of the UniProt accession numbers and minimizing the space these need in the memory representation. So he's really gone to a very high level of optimization, which of course goes against flexibility in quickly adjusting it to something else.
Yeah. So
it's possible, but it's a major project. It's harder than you would think intuitively.
This is what I always explain to people when we are talking about the code, because sometimes the finalized code is like, oh, but this looks very difficult to follow, and then I say, well, when I started, it was very easy to follow, but every time that I try to improve, every time that I try to squeeze 10 milliseconds here and there, the code gets more complicated, and the data structures for data representation gets more complicated. So the level, as Henning says, the level of specialization of the analysis tool is so high for the Reactome data that maybe we should step a little bit back just to have a broader analysis tool, which is okay. But right now we are achieving times of 150 or 200 milliseconds for the normal data sets that maybe would be penalized by quite the double of this time if we just get into a, let's say, less specialized data structures and data formats. Yeah.
That makes perfect sense. Figured the answer would be something like that. So I'm sorry if I could follow up with one more question then. I mean, perhaps a simpler integration, right? BioGPS has gene lists. I think COPA-KB has gene lists or protein lists, right? There's, I assume, some technical mechanism just to say, hey, for us to launch or send that gene list into a pathway analysis.
Mm-hmm.
Antonio.
Yeah, sure. Yes,
that exists.
That already exists. So the analysis service is a RESTful service where the final user can just send the data, and then we'll receive the result with a token associated. And then there are several methods that are helping the final user to dig the data depending on what the aim is. The nice thing is that supports the course implementation. That means that you can create your own lightweight client in your as a web application, for example, and it can run without the need of any proxy or anything in your server side. Or you can use it from your server side if you want to integrate it in a pipeline. And I can share actually in the
just demo it. We are in the screen sharing.
Yes.
Just demo it in real life with Intec or Flight.
Okay, that's a good point. Let's see if I.
Can you still see the screen share?
Yep.
Do you see the browser now?
Yes.
Slash Intec.
Oh,
right. You can take. I'm not sure if it's on Flight or on the www.
it's possible to.
It's really hard.
It's nice to see that these guys are changing.
Let's see if I can find something. So, okay.
So maybe I mean I
So basically, what we can go to Intec. Go to the Intec one. Go to the Intec one. We can at least show it. Okay. So now if we do this. So this is just binary interactions for a given protein. Then you go. Oops, what do I do now?
Actually, because this is a nice feature that if you double tap.
Okay. So now try again. I want to go to lists. Now I get the list of proteins which are in this interaction set. I click and select all, and then I click on pathways. And this is now, I think there will be still a known bug which we fixed this morning, but basically all you do is you click and it sends the list of proteins to the Reactome pathway analysis, and then you click on view pathways, and you get then into the results of the pathway analysis, and the bug is now going to be fixed by Antonio. There's just a URL error, and then you get into the results. So you can directly from any application with little effort send a gene or protein list to the analysis, and then you link directly into that.
Great, fantastic. That's cool.
And as you've seen, it's rather fast. So you can send a genome-wide list, something like thousands of identifiers, and it's interactive speed.
Great.
Yeah, there are different projects that are already integrating this, like the Blueprint, Pride, Intact does it. Also, Copa KB, I think they integrated this analysis. I don't think it's available online yet, but at least they did it in the past.
And we also used, staying on the topic of analysis, we did another sort of little project benefiting from this, which is integration with biomodels. So we have a sister database which stores systems biology models. So basically, well, I always say it's a pathway with mathematical formalism and chemical rate constants and so on added, and is then really an executable predictive model. And in the biomodels database, we have around 1,000 models. And we, in this project, we just extracted from these models all the protein and chemical identifiers, and then treated these as gene lists, ran them against the Reactome pathway analysis, and used that to establish pairwise cross-references from Reactome pathways to the best matching models, and the other way around. So, and this is exactly what Andrew said. We just considered it as gene lists. We are abstracting from the more complicated structure.
Just if you want, going very quickly, this is the interface of the RESTful service. It has 5 sections. The sections, just to send data to the analysis would be rather identifier if you have a single identifier, which is not very good for data analysis, but identifiers would be a good way just to send your data. Then there are different ways. Basically, is if the user has a file, should use the interface form. If just wants to send a bunch of identifiers via post, is via the identifiers method. And then and then a URL is because you can have your data. This is the case of Intact, Bright, and all of this. That you have your data hosted in your server, and then you want to provide a URI to this file, to the analysis. So then is the analysis the one that goes and download the file, analyze it, and sends back to the user the result. This is good because it means that in your client you don't have to download the data. If it's a web application, you don't have to download your data into the client, so the client posts it to the analysis service. You just send where the data is hosted, and the analysis service will download it. The advantage is that normally between servers there is better bandwidth than between clients and servers, and then you take advantage of this also for the speed of the analysis. All of these three methods have this projection option. This is the option that is used to project the data to human, in case you are submitting data of other species and you want to see the result projected to human. Now I will show you.
So this is an orthology-based projection.
Yes.
And this is done because Reactome is annotated on human only, and is all the other Reactome species are based on orthology inference. So you can instead decide to do the projection to human because that's the richest part of Reactome.
Yeah. Now I will show you an example using the identifier method. In this, when I've opened it, this is a little bit of documentation on how the result is retrieved, and this is the data format. This is what you have to. This is what the data looks like when it's retrieved from the server. For the example, I will just paste. I just copied this from other examples that I had in here, and then I will put like test 32K demo test as the name of the sample. This is all configurable, but by default you can just try it out and it will work. And this was the actual time for the analysis. So this is it. This is the result, and this is the token that is being associated to this analysis. Now if we go, and then in the summary we see that this is an overrepresentation because you don't need to specify the type of the analysis. The analyzer will identify the format of the data that you have sent, and will understand which is the type of analysis that needs to be executed. The sample name is the text that I wrote there, and then this is other information that needs to be taken into account. And then here we have that the number of pathways found are 5,140, and now the result, if you don't specify any different thing from the default, this is the most reliable pathway, and then you can see here all the results for this pathway, and then the second pathway, and so on. And by using this token, and going to the set of methods that are based on token, so further queries you could filter by pathways or filter by species. In the case that you have sent a sample from several species and you have them project to human, and and other options just in case you want to have a table with the results and then you want to paste the table and so on, and the different options. So the user can use these different methods as any other RESTful service, and that's it.
Perfect. Yeah, that looks great. Thanks. Well, I'm going to create a ticket to hook up BioGPS via this mechanism.